So this viscosity is under properties of matter. This is the second subunit under properties of matter. Okay. So this is a very important lesson, actually a subunit under the properties of matter. You can easily gain marks once you learn this 10th unit, that is properties of matter, right? Okay. So viscosity. So meaning of viscosity, this is regarding friction between liquids, right? I know that you have learned friction, right? So that friction, the friction you learned earlier is regarding solid surfaces, right? Solid surfaces. So if you, let's say this is the surface, and if you try to move this object, a friction occurs to the other side, opposite side. Friction always opposes, right? Opposes the motion. So this is between solid surfaces. Okay, that is F equals mu r. You can apply mu r, but that is only for solid surfaces. But in this lesson, it is about friction between liquid layers, right? Friction between liquid layers. So when you consider a liquid, let's say this is a liquid that is flowing, right? Liquid flowing. You can imagine liquid layers like this. These are hypothetical layers, right? You can hypothetically separate that liquid flow into layers. Then between these layers, there is friction. So in this lesson, that is what we are talking about. Friction between liquid layers, okay? So let's say you have two liquids. One liquid is water. So water can easily flow, right? Water can easily flow, meaning it has less friction, it has less viscosity. If you consider like trickle or honey, let's say honey. If you consider about a honey flow, it is hard to flow, right? That flow is like very hard. So the viscosity of honey or trickle is high. So okay, so we can say friction between honey layers is high compared to water. Okay, so that is something we are going to talk about. First, just take down this note, and as I'm reading, you have to understand this note, right? Okay, take this down. When an object, take this down. When an object moves in water, when an object moves in water, water causes a resistance to the motion of object. Resistance to the motion of object. Full stop. This explains that water can produce a certain type of friction. A certain type of friction. Commonly, another sentence, right? Commonly, comma, this property this property in liquids and gases. In liquids and gases is called viscosity. Is called viscosity. Another sentence. Viscosity of liquids. Viscosity of liquids like water. Like water. Comma, water, comma, glycerin. You know glycerin, right? Glycerin. Water, comma, glycerin is less and viscosity of and same sentence, right? And viscosity of liquids like honey, paint trickle, right? Honey and tar. Honey and tar, right? You know tar, right? Honey and tar is larger, or higher, right? Is higher. Okay. So water and glycerin done, right? Did you miss any part? No, right? Okay. So water and glycerin, the basic meaning is water and glycerin has low viscosity. Then honey and tar has high viscosity, right? So these are like hard to flow, right? These are easily can have a flow, right? So that is the basic idea of viscosity, right? Now I think you have a kind of like a rough idea of viscosity now, right? Then we are going to move into equations. We need to quantify viscosity, right? So to quantify viscosity, we need Newton. So Newton has an equation to quantify viscosity, right? To quantify viscosity. Write this subtopic, viscous force and Newton's equation. Take this down. That is a subtopic. Viscous force and Newton's equation. Okay. So I am giving you a perfect note, right? So clearly you have to write this, take this down, take this note. Okay. Did you write this viscous force and Newton's equation? So here as well, Newton has an equation, right? Even for the viscosity as well. So throughout the whole syllabus, you have Newton, right? Yeah. Under this, write down, consider a liquid flowing on a static plate. Consider a liquid flowing on a static plate. Here, next sentence, right? Here, comma, the liquid flow is steady and streamlined. Liquid flow is steady and streamlined. Steady and streamlined. So you know steady and streamlined, right? From hydrodynamics, you know that steady and streamlined means it is not turbulent. So none of these equations can be applied for turbulent flows, right? Turbulent means there's no order there for the flow. These are turbulent. For streamline flows, you can draw these streamlines. Okay, I'm not going to explain too much that. These are called streamline flows. So those Bernoulli equation also can be applied only for flows like this, right? These equations also only for flows, streamline flows. Okay, right. Okay, so we have this static plate, let's say a metal plate, right? This is a cross section, metal plate. Static means this is at rest. This is at rest. Then over that plate, there's a viscous liquid flowing. Viscous liquid flowing. Okay. So what happens? The liquid layer that is in contact with the plate is at rest. That is what we say, right? If plate is like this and if there's a liquid layer right above that layer, it is at rest with the plate. It is like stick to the plate, right? So we say velocity of this is 0. This liquid layer has a 0 velocity. Then this arrow shows the magnitude of the velocities, right? Then what happens as it goes up away from the plate, velocity gradually increases like this. And the top layer has the highest speed. Top layer has the highest speed. Then I'm going to get two layers, right? Let's say P and Q layers. This is a one layer and there's a Q layer named Q. Okay. So velocity gradually increases as you go up. Okay. So this is like let's say a tunnel or something. Tunnel. You take a cross section of the tunnel. So this is at rest, but as you go up, the bottom layer is at rest. As you go up, velocity gradually increases and the top layer has the maximum velocity. Okay. So gradually increases. Then I'm getting two layers, P layer and Q layer. I'll enlarge those layers like this. If you get a 3D image of that layer, this is one layer, right? Let's say that is P. Then below that, there's Q. Q layer. This is Q. As you can see, this has a higher velocity. Let's say that velocity of this layer is V1. Bottom is this layer is V2. We know that V1 is larger than V2, right? As you go away, velocity increases, right? And if the gap between these two layers is D, these are two layers like this, right? P and Q. Gap between these layers is simple D. and top layer has a higher velocity, bottom layer has a less velocity. And the gap is d. Then we can consider an area. This area is called common area, right? Common area means if you have two layers like this, let's say this layer is above that, right? Common area is this much. Understood? Not the whole thing, just the common area, right? Just take this, draw these two quickly. Thumbs up once you're done drawing, right? Take these two. Thumbs up, right, if you done with the drawing. Okay, did you draw, Amani? Okay, right. Now take down this. I'll explain. I'll give you this on a note, right? Okay, write down liquid layer in contact with static plate. Liquid layer in contact with static plate is at rest. Within brackets v equals 0. And when goes up, velocities of consecutive, means adjacent, right? Consecutive liquid layers gradually increases. Okay, gradually increases. Full stop. Maximum velocity is at the top layer. Maximum velocity is at the top layer. Maximum velocity is at the top layer. Another sentence. Due to difference of velocity of P and Q layers it causes a relative motion between them. It causes a relative motion between them. Another sentence. This causes a resistive force against the motion. this causes a resistive force against the motion. Uh, then write another sentence. This is viscous force. This is viscous force. Within brackets, capital F. This is viscous force. Okay? Done, right? Right. Okay. So I'm talking about these two layers now, right? These two layers. Here what happens? Let's say this bottom layer moves at 1 meters per second. This layer moves at 10 meters per second. Then what happens? As it goes up, as it moves, this is trying to slip over this layer, right? At 9 meters per second. There's a relative motion. There's a relative to this layer. There's a velocity to this. Since that is the same side, it is 9 meters per second, right? This is moving at 9 meters per second relative to this. Okay. If this moves 1 meter, this is trying to move 10 meters. So obviously the above layer has to slip over that, right? So this layer is trying to move to this side. So the friction on this layer is to the opposite side. There's a friction causing to the opposite side. Because this is trying to move to this side, right? By this layer, on top layer, there's a friction force acting to this. This friction is what we call viscous force. Okay? This is actually friction, but in this lesson we call this viscous force. Then reaction force of this viscous force at the bottom layer is to this opposite side. So here we are going to apply an equation, we call that Newton's equation, to quantify this capital F, this viscous force, right? That is the next step. Just mark this F as well on your image, right? This F. At the top layer, F is to this side, bottom layer, F is to this side, right? These are action and reaction forces actually. Did you mark that? Just mark this F. If you don't understand something, please use the chat box, right? Okay. Below the note, just continue the note like this. Write down the viscous force within brackets capital F, the viscous force capital F is proportional to quantities below. Quantities below. Quantities below. Below that, right? First one, number one, common area. Common area in contact with liquid layers. Common area in contact with liquid layers. Number one, common area in contact with liquid layers. Within brackets, capital A. And then second quantity. Write down velocity difference alone perpendicular unit length, perpendicular unit length, velocity difference alone a perpendicular unit length, or velocity gradient, or velocity gradient, or velocity gradient. So what is velocity gradient? Within brackets write this one, v1 minus v2 divided by d. This is what we call velocity gradient. v1 minus v2 divided by d. That is velocity difference per unit length, right? When you divide it by length, velocity difference per unit length. So these are the A and this one. That is within brackets, right? Take it down. So if you think about this one, this is V1, V2, and gap between that is D. When you divide it by the gap, we call that velocity gradient. Actually, this has a constant velocity gradient, right? Okay. Done, right? So those are the two quantities that viscous force depends on, right? So that is found by Newton, okay? So according to those, we can write this equation like this. So viscous force is proportional, not equal, right? Is proportional to what? Common area A. What is the another one? Velocity gradient. Okay? So that is what Newton says. Common area and velocity gradient. So you can write that as a multiplication. Just proportional, right? Then if you want to write this as an equation, you have to put a constant. You can make it an equation, put constant. This constant is called eta. Earlier you have used to use this for efficiency, but here it is for this constant, right? Eta, then A, V1 minus V2 divided by D. This equation you must remember. So this is the Newton's equation for viscosity. Just take these two down. If you have any problem, let me know. Just take these two down. Done? Right. Below this, right? Here, eta, here, comma, eta is called, here, eta is called coefficient of viscosity of liquid. Coefficient of viscosity of liquid. Coefficient of viscosity of liquid, right? So eta is called coefficient of viscosity, okay? That constant. Then write a subtopic, definition of eta. So we are going to need a definition for eta. So write down subtopic definition of eta. So this is how you write it. When this is 1, let's say velocity gradient is 1, right? and the common area also is 1. So if we take unit gradient, taking something to be equal to 1 means we are considering a unit of that, 1 unit of that, right? If velocity gradient is 1 and A is 1, common area is 1, then just substitute these are in the equation. So A is 1, velocity gradient also is 1, right? So eta is, so under these cases, viscous force is what we call eta, right? Take this down. Definition of eta. Take this down quickly. Right. So I'm going to describe this under this, right? This eta thing, right? These sentences are like really important, right? You have to read these again and again. The notes, the note I'm giving you, right? The more you read these, the more you will be able to understand these concepts. Okay. Write down. In an area, in an area, in an area where, in an area where velocity gradient of a steady streamline flow, steady streamline flow velocity gradient of a steady streamline flow is a 1 unit, comma, viscous force acting on a unit area that is parallel, right? Parallel to liquid flow, parallel to liquid flow is the coefficient of the liquid, sorry, coefficient is the viscous coefficient, right? Is the viscous coefficient of the liquid, is the liquid coefficient of the liquid. Done. So that is the explanation of viscous coefficient, right? When these are 1, force, this force is equal to the viscous coefficient, right? So that explains the whole thing, right? Okay. Wait. Okay. So now we have the equation, right? So that is the equation we are going to use, the main equation for the whole thing, right? There are a few equations, but this is the main equation. Other equations are derivatives of this main equation actually. Then we are going to consider about units and dimensions, right, of this. Okay, so what is the equation? You must remember this: F equals eta A V1 minus V2 divided by D. So this is the equation. So I am going to find dimensions of this coefficient, viscous coefficient. So how do we do that? First step, just subject eta. So F D, cross multiply, right? FD divided by A V1 minus V2. So that is eta, right? Then I'm going to find dimensions. Can you find the dimensions of this and let me know the answer? Quickly, right? Take this down first, then find the dimensions. I need dimensions for eta, okay? Let me know the answer, the dimensions. I think you know dimensions, right? Quickly, right? Take this down and find the dimensions. It doesn't matter that you get the wrong answer, but someone please find the dimensions and let me know. If you have any problem, let me know as well. I need you to engage, right? Okay, right. Let's see. So force mlt minus 2, right? F equals ma. So m, this is acceleration. mlt minus 2, that is force. D is a length. This is area, so length squared. This is a velocity. Velocity difference means just a velocity, right? So that is LT minus 1. Now you have to simplify this. So there's L is squared, which cancels with this one. But there's a length here. That length goes up, L minus 1. T minus 2, T minus 1, T minus 1. So this is the dimensions of eta. M, L minus 1, T minus 1. That is the, yeah, correct. So that is the dimensions of viscous coefficient, right? Then I'll write dimensions, units using fundamental. Based on fundamental units. Let's write that. So based on fundamental units, what? When you look at the dimensions, this is kilogram. This is per meter. This is per second, right? All these are based on fundamental units. Remember? Fundamental units. Another thing, we can have derivative units. Based on derivative units. So how can we find that? Eta. So here we have what? Newton. This is square meter area. Velocity gradient means meters per second divided by meter. So this velocity gradient has a per second, right? If you don't understand, let me know. Velocity gradient has per second. Area square meter. Then what do you get? Write these terms at the other side. Newton equals eta unit times meter squared per second. When per second goes to this side, it becomes Newton second, right? Then square meter. Got it? So that is the derivative unit. Derivative unit, right? You don't have to write this. You don't have to write this, right? So another one, Newton second meter squared. There's another unit, joule second meter cube as well, right? Okay, write this down. Take this down. The units. So there are 2 units, right? You can have another unit as well. Newtons per square meter means Pascal, right? Pascal second also is a unit of coefficient of viscosity. Take this down. So if they are based on fundamental units, you have to write this one. These are based on derivative units, right? Take this down. Thumbs up, right? When you take it down. Sahil, did you take it down? Okay, right. So I'm going to ask a question, right? Now you know somewhat about this eta. What do you think? When temperature increases, what could happen? Does the viscosity decreases or increases? I mean, not viscosity, viscous coefficient. Does it increase or decrease? Let me know. When temperature increases, what could happen? Just guess, right? Does it increase or decrease? Everyone? When temperature increases, does the viscous coefficient increase or decrease? Decreases, right? Decreases. That's not increase. So you know that when you take honey and if you increase the temperature, is it easy to flow or difficult to flow? When you increase the temperature, it easily flows, right? What does it mean? Viscosity has gone down as the temperature increases. So is the viscous coefficient. Same thing happens to the viscous coefficient. Viscous coefficient represents the viscosity, right? So when temperature increases, viscous coefficient decreases. Take this down, put asterisk mark, write down when temperature increases, when temperature increases, when temperature increases, eta of liquids decreases. Eta of liquids decreases. Below that, right? Therefore, eta of liquids is mentioned. Eta of liquids is mentioned with temperature. Is mentioned with temperature. Got it? So eta is dependent on temperature, right? Like kind of like everything, not everything. Almost all the quantities depends on the temperature, right? Not all, right? I mean, most of the when you are thinking about matter, the properties of those depends on temperature, right? So is eta, right? Then below that we'll write that examples for few viscosities, right? So you have to mention the temperature at, this is at, right? At 15 centigrades. So I'm going to give you viscous coefficients, examples of viscous coefficient. You have to mention the temperature, right? So these are at 15 centimeters, sorry, centigrades. Eta, with me, write this, take this down with me, write everything, right? Eta water 10 to the power 3 minus 3 ns per square meter. Then eta mercury 1.5 10 to the power minus 3 ns per square meter. Then eta honey 100 Newton second per square meter. So these are the viscous coefficients of few liquids, of a few liquids. Take this down. Done, right? Okay, then there is a question. Take this question down because I need to add this question to the theory note, right? That's why I'm reading your question. Write down Q1. This question explains the theory, right? That's why I'm giving you this. Write down to the same note, right? Q1, question 1. On a horizontal plane, quickly take it down. On a horizontal plane, Q1, on a horizontal plane, a liquid with viscous coefficient, a liquid with viscous coefficient this value 1.2 10 to the power minus 3 ns per square meter, viscous coefficient 1.2 on this value, is applied to a thickness 2 millimeters, to a thickness 2 millimeters. Full stop. On it, comma, a cube with side length, 10 centimeter, side length 10 centimeter, is moved at 2 meters per second. 2 meters per second of uniform velocity. Full stop. Find the horizontal force required for this. Find the horizontal force required for this. Done? Okay. So this is what happens, right? On a horizontal plane. So this is a cross section, this is the horizontal plane. Liquid is applied to 2 millimeters. The thickness of the liquid is 2 millimeters, right? This is the liquid. Then on that liquid there is an object, cube. So what happens? This cube needs to be moved at 2 meters per second, right? So what they ask is force required. Let's say that force is P. What they ask is force required. Let's say that is P, right? Okay. So the Newton's equation, not F equals m, right? What I just described. You apply that to this liquid layer. You apply that to liquid layer, right? Not to the object. So if this object needs to be moved at constant velocity, you know that when you apply this P force by the liquid on the object, there's a friction force. That is the viscous force, right? Capital F acting on to the other side. To have a uniform velocity, you have to, this P is should be equal to F, right? So if you find F, meaning of that is you found P, right? So you know P and F is equal. Then apply the equation. What is the equation? Eta A V1 minus V2 divided by D. Then you have to substitute values. So what is eta? 1.2 10 to the power minus 3. Area is given, right? So what is the area? If you consider the cube, what's the bottom of the area of the bottom? Once you have to substitute in meters, right? 10 centimeter means 0.1 meter, right? You have to divide by 100 to convert into meters. 0.1 meters, right? 0.1 meter into 0.1. This is the area, A. Then the velocity. What's the velocity here? Do you remember? This is a solid surface. The liquid layer in contact with the solid surface has the same velocity as the solid surface. So solid surface has a 2 meters per second, and so is liquid layer in contact here. So that is V1, right? Here the velocity of the liquid layer is 0. That is V2. This point, it is at rest. So just substitute values. V1 is 2 minus 0 divided by D. D is 2 millimeters. Convert into meters, you have to multiply by 10 to the power minus 3. Right? Then you have to simplify these. Okay, take it down. If you have any problem, let me know, right? 2 cancels off. You can easily simplify this. This 10 to the power minus 3, 10 to the power minus 3 cancels off. 10 to the power minus 1, minus 1, minus 2. 0.012 Newton. So this is the force required for that, right? These are very small forces, right? You know, liquids cannot apply those large forces like solid surfaces. So these are small forces, right? Okay, take it down. Thumbs up, right? Once you take it down. Thumbs up, right? If you complete. So no issue with this one, right? No issue, right? Okay. Uh, so why did I do this question on the note? To show that these forces are very small, right? Those friction forces due to liquids. If there was no liquid here, if there's no liquid here, what could happen? These forces are like 10 Newton, 20 Newton. So those forces, those friction forces are between uh, solid surfaces, right? Between solid surfaces. But these are very small, right? Compared to the friction forces between solid surfaces. Okay, right. Put an asterisk mark. Write this down. To decrease, to decrease the friction between, to decrease the friction between mechanical parts, comma, lubricant, lubricant oils, lubricant oils, lubricant oils are used, lubricant oils are used, full stop. Since, next sentence, right? Since viscosity decreases, viscosity decreases when using, when using, comma, lubricants, lubricants needs to be changed, lubricants needs to be changed. Lubricants needs to be changed. Okay. So that's why we use lubricants, right? For mechanical parts, you know, in a vehicle or some kind of that, we always use a lubricant, some kind of a oil, right? Kind of like engine oil, those stuff. The reason is to decrease the friction between those parts. That's the reason, right? So that is a okay. Now I think you have some kind of understanding of Newton's equation, right? Then the next part, then there's going to be another scientist giving you a equation, right? That's the next part. Write down Poiseuille. Take this down. Poiseuille's, this is another scientist equation. Take this down. Poiseuille's equation. Right? First take this down, then I'll explain, right? Take this down. Consider that a liquid, consider that a liquid flows through a horizontal capillary tube. Horizontal capillary tube. Underline horizontal, right? Consider that a liquid flows through a horizontal capillary tube under steady streamline, under steady streamline conditions, under steady streamline conditions, full stop. right? So here, this Poiseuille's equation, right? You had Bernoulli's equation, but that Bernoulli's equation can only be applied for non-viscous liquids. For non-viscous liquids only, that Bernoulli, right? Remember? Because that's the energy equation, right? Viscous, if there's friction, you cannot apply Bernoulli's equation. But here we are talking about liquids with friction, right? So we need another equation. You cannot apply Bernoulli's equation here for these questions, right? If it is a viscous liquid. Yeah. There are some conditions you have to remember that so here we are talking about liquid flows through pipes. Viscous liquid flows through pipes, right? Pipes, thin pipes actually, right? And these pipes must be horizontal, right? If it is inclined, if the pipes are like inclined, you cannot apply. Those should be horizontal, right? In order to apply this equation. And also, you cannot have a turbulent flow inside the pipe. The flow should be steady and streamlined. Okay? Let's say this is the pipe. Horizontal, right? Here you have the pressure P1. At this end, there's a pressure P1. And another end, P2. In order to flow a viscous liquid, you must have a pressure difference, right? So let's say this P1 is larger. So the liquid is pushed to this side. If we consider the velocity profile of the liquid, you know that with the pipe, velocity is 0, right? Here velocity is 0, but as it goes to the middle, velocity gradually increases. So the velocity profile would look like this, right? This is called velocity profile. Profile means velocity of each particle at each point. The length of the arrow shows the magnitude of the velocity. So you can see right at the center, it has the maximum velocity. Okay. Then the another thing, length of the pipe. Let's say length of the pipe is simple L. And radius of the pipe, simple A. I'm taking radius of the pipe to be simple A, right? So we are going to build that equation, right? Okay. Just take this down. Take this down. Thumbs up, right? Take this down. Right. Take down this note. Below that, right? Velocity of liquid layer. Velocity of liquid layer in contact with inner walls, not walls, inner wall, right? Velocity of liquid layer in contact with inner wall of tube is 0. Right? Now listen, right? Do you understand the liquid layers in a moving through a pipe? What's the shape? Those are cylindrical shapes, right? This is a one layer. This layer. Inside that there's another layer. Got it? Do you understand those liquid layers? Cylindrical liquid layers, right? There's a liquid layer in contact with the tube. So that liquid layer has 0 velocity, right? Around that tube with the inner walls of the tube. It has 0 velocity. As you gradually goes towards the center, towards the axis of the tube, the velocities of layers increases, right? And the layer along the axis has the maximum speed, right? Okay, to the same note, write down towards the axis, towards the axis, towards the axis, comma, velocity gradually increases. Velocity gradually increases. Towards the axis, velocity gradually increases. And velocity is maximum. Velocity is maximum along the axis. Velocity is maximum along the axis. Right? Below that, write another sentence. Volume of liquid, write down volume of liquid flow, volume of liquid flow through the tube, through the tube through the tube per unit time, per unit time or volume flow rate, or volume flow rate. Within brackets, right? Volume flow rate within brackets, we call that Q. Okay. Or this is not velocity, this is volume. Volume divided by time, right? That is the volume flow rate. Volume divided by time. Write down this to the same note, right? Volume flow rate within brackets, this depends on the quantities below. The quantities below. Right? So same as before, these are experimental results, right? Actually, Poiseuille found these, right? The scientist Poiseuille found these. Volume flow rate. Volume flow rate means what? Cubic meters per second, right? Volume divided by time. How much of a volume of liquid flows within a given time, right? Let's say 5 liters flows within a second, right? So the flow rate is 5 liters per second, like that, right? So we are going to get an equation to find the volume flow rate through this pipe, through this tube. Okay, so Poiseuille has found these properties. First one, write this with me, right? Viscous coefficient of liquid, eta. Write this down. First one, viscous coefficient of liquid, eta. Second one, radius of tube, simple A. Radius of tube, simple A. That is the second one, right? Radius of tube, simple A. Third one, pressure difference across a unit length. Pressure difference across a unit length. Pressure difference across a unit length. Or pressure gradient. Done. Pressure gradient. So do you remember velocity gradient? What did we do? We just take velocity at two places, then divide by the gap, right? Length. To find the pressure gradient, what do? We take the pressure difference here. What is that? P1 minus P2, right? P1 is greater. P1 minus P2 and divide by the length. Here it is length, right? P1 minus P2 divided by length. So this is pressure gradient. For P1 minus P2, if you want, you can say it like delta P. Pressure difference, delta P, divided by length. Take it down. Okay. Now I am going to find dimensions of pressure gradient, right? So this is pressure gradient. What are the dimensions? What is the, just find that, dimensions of pressure gradient. Dimensions of pressure divided by length, right? Just find that and let me know the answer. Someone? Okay. So the pressure, right? Pressure is force mLT minus 2 divided by area, L squared. So when you simplify this, what do you get? mL minus T minus 2. So that's the dimensions of pressure. divide by length. So what do you get? ML goes up minus 2 t minus 2. Okay, take it down. Under that, right, combination between, write down, right, combination between these, can be built, using dimensionless, right, can be built using dimensional analysis. Underline dimensional analysis, right? Okay. So I think you have done this like when you are learning dimensional analysis as well. So for the completion, I'll do that, right? Okay. So according to a Poiseuille's combination, right? Flow rate, we denote that as capital Q. Q depends on what? They say proportional to viscous coefficient, right? Then what? Radius. But we don't know the power of that, right? We don't know whether it is squared, cube to the fourth power. We don't know that, right? So we mention the power here, eta x. Then a to the power y. Another one, what is the another one? Pressure gradient. Delta P divided by L to the power, let's say Z. So if you find X, Y, and Z, that is dimensional analysis, right? You can build the Poiseuille's equation. Take this down. Take this down. Then you can write the equation, right? To write the equation, you have to put K. That is a constant. Eta x, ay, delta p divided by length, is it? This K is dimensionless, right? Dimensionless constant. Okay. We use a K, and we know that K is a dimensionless constant, right? We have to put a K to make it an equation. That is a dimensionless constant. Okay. So in order to find X, Y, and Z, what should we do? You have to say that both sides has the same dimensions. So what is Q? Q is volume flow rate. Volume divided by time, right? Volume divided by time is volume flow rate. So what is volume? L cube divided by time, t minus 1. K is dimensionless, so we can disregard that. Eta, remember what's the dimensions of eta? If you don't remember, you can check that. ml minus 1, t minus 1 to the power x. Then radius, that is a length, right? So y. Then what is the dimensions of delta p over L? We found that earlier, right? What is that? ml minus 2, sorry, ml minus 2 t minus 2, right? We don't have a term for m here, mass, so we can say m naught, right? M naught means 1, right? Okay, then what do we do? Then you have to simplify this, cube t minus 1, m, that is x, there's a 1 here, x plus 1, okay? L means minus x plus y, there's a z term also, right? To the power z here. X plus z actually. For m, x plus z. For L, minus x plus y minus 2z. You have to carefully do this, right? If you make a one mistake, then you will get a completely different answer there. So those are for L. Then T. For T, what do you get? Minus x minus 2z. Okay, take this down. Take this down. Okay. Right. Then for m, right? For m, you have to compare the powers of m. So here we have 0. Then we have x plus z. X plus z, right? Then for L, we have what? 3 equals minus x plus y minus 2z. Then we have t. What do you get? Minus 1 equals minus x minus 2z. These are simultaneous equations. Simplify these and let me know the answer. Find x, y, z. Let me know the answer. Just find x, y, and z, right? X, y, and z. And let me know the answer for x, y, and z. Simple A means radius, right? Not it is a length. Simple A does not mean area, it is a radius. Okay, quickly find x, y, and z. It's 3 simultaneous equations, right? You have to find x, y, and z. So x is minus 1, right? Y is 4. Z is 1. Got that? Yeah. Okay, correct. Right. Now you know the powers, right? Powers of each term. You know the powers of each term. What can you do now? Now you just have to substitute. So what do you get? Q equals, we have K for eta x is minus 1. Y is 4 to the power 4. This is radius, right? Not area. This is radius, simple A. Then delta P divided by length. Is it? That is 1. Okay. Okay, write this down. Okay, now you have built Poiseuille's equation, right? Using dimensional analysis. Write this down. Thumbs up once done. Under that write, it is found that K equals 5 over 8. It is found that K equals 5 over 8 experimentally. It is found that K equals 5 over 8 experimentally. So now what can you say? Only way to, you cannot find K using dimensional analysis, right? You have to go for an experiment in order to find this K. So it is found 5 over 8. Now you are going to have the complete equation. K is 5 over 8. This eta should be below, right? I'm going to write delta P here, A to the power 4. This eta goes below, right? To the denominator. And length is at the denominator already. Okay, this is what we call Poiseuille's equation. This Q is volume flow rate, right? Is equal to pi over 8 delta P A to the power 4 eta L. You must remember this, right? They don't give you this equation. You have to remember this. Must, right? Take this down. Okay, below this write down, this is the Poiseuille's equation. This is the Poiseuille's equation. For the equation to be valid, comma, for the equation to be valid, comma, first one, right? First condition, right? Flow should be steady. Flow should be steady and streamline. Flow should be steady and streamline. Then second one, tube is horizontal. Tube should be horizontal, right? We cannot have this for inclined tubes. Tube should be horizontal. Third one, tube should be thin. So usually we apply these for thin tubes, right? Tube should be thin, like capillary tubes, right? We can apply Bernoulli equation without any problem. Tube should be thin. Okay. We'll go for a question. Take this down. There are questions in the tube for you to practice, right? I'll discuss them as well, but I need this question in the note, right? Okay, write down Q. Take it down. Radius of a capillary tube. Radius of a capillary tube is 2 millimeters. Is 2 millimeters. And length is 20 centimeters. Length is 20 centimeters. Full stop. A liquid with viscous coefficient. A liquid with viscous coefficient. This value 1.5 10 to the power minus 3 ns per square meter. 1.5 10 to the power minus 3 ns square per square meter. Flows through it. Flows through it. Full stop. Flow rate is that is Q, right? 60 cubic centimeters per second. Flow rate is 60 cubic centimeters per second. Full stop. Find the pressure difference. Find the pressure difference across the tube. Find the pressure difference across the tube. Okay. Okay, just try that. Delta P. You have to find delta P, right? Just write the equation, then substitute values. But you have to convert these units, right? Into meters, seconds, those stuff. Try that. You just have to substitute values. First write the equation. Then substitute values. Do that, right? So 60 cubic centimeters. You have to make it meters. Centimeter converted into meters. 10 to the power minus 2. It gets cubed. 10 to the power minus 6. Five means 22 over 7. 1 over 8. Radius 2 millimeters. 2 times 10 to the power minus 3 to the power 4, right? Divided by eta. 1.5 10 to the power minus 3. Length 20 centimeter means 0.2 meters. You have to simplify this, right? So this is the substitution, and there's delta p. Okay. So at home, find the value for delta p, right? Take this down. At home, find the value for delta p. So under that pressure reference, we'll have this much of a volume flow rate. Did you take this down? Leave a space for delta p, right? To write the value of delta p. Right. Then there's one more theory, pipe systems in series under this Poiseuille's equation. Once that Poiseuille's equation is done, right? Then we have to go for doing questions on the tute. Then for this lesson, there is a Stokes equation, right? Stokes equation, that is the another scientist. So this lesson is based on like 3 scientists, right? Another one is a Stokes equation. So with that equation, once we did that, we can complete this lesson, right? Stokes equation, then there's going to be based, there are derivatives of Stokes equation. We'll go for like terminal velocity, stuff like that, right? Yeah. So tomorrow at 8 p.m. I'll do that. You have to get ready for this. At least you have to read this and try, or you can write, if you want, you can write it like a separate note as well. So anyway, study well this note, right? So I think all of you are 25 batch, right? 25 batch or 24? Can you 25 everyone, right? I think. Yeah. So this is, this is the 10th unit, right? But covering this earlier is going to be, is it hugely beneficial for you, right? Covering this earlier. Because at the end, they will quickly cover this unit. You won't be able to catch that up, right? This unit has a lot of marks. You will understand the value of this closer to the exam, right?